So, lecture 9 of algebra. And I think the last thing I did on Wednesday last week was the Chinese remainder theorem. And it's a beautiful result, very old, which says the following. Let A and B be positive integers that are relatively prime. So the GCD of A and B is equal to 1. The greatest common divisor is 1. And let alpha and beta be any integers, positive, negative, or 0. There exists an integer x which is simultaneously satisfying two congruences. X is congruent to alpha mod A, and at the same number x is congruent to beta mod B. And moreover, x is unique modulo the product of A times B. And what that means is if x prime is another number which is congruent to alpha mod A, and x prime is also congruent to beta mod B, then in fact x and x prime are congruent modulo the product A times B. And the proof, well, there's several ways to prove it. Here is one. So if x and y are relatively prime, then that means, if A and B, the moduli, are relatively prime, then there exist integers, call them U and V, integers, such that one is equal to, or let me maybe follow the notation of the book, call them integers S and T, such that one can be written as S times A plus T times B. So if I multiply this equation by, for example, alpha minus beta minus alpha, beta minus alpha is beta minus alpha times SA plus TB, which is beta minus alpha S times A plus beta minus alpha T times B. And let me call this number X and this number Y. So this is XA plus YB. So what I just proved is that if A and B are relatively prime, then I can write beta minus alpha as some integral linear combination XA. Well, let me call this U. UA and VY, UA and VB. So if A and B are relatively prime, in fact, every integer is some integral linear combination of them. So they're integers U and V such that beta minus alpha is UA plus VB, or beta is equal to alpha plus UA plus V times B. So suppose I let X be equal to this number, alpha plus UA. Then immediately this says that X minus alpha is divisible by A. So X is congruent to alpha mod A. But from this equation, which is beta equals alpha plus UA, that's X plus VB, that means X is also congruent to beta mod B. So that's half of the proof. Any questions about this?
Professor, I have a question for the when we have a midterm, are we gonna use actual numbers or do you want us to show the proof like this?
Oh, you have to show proofs.
Okay.
I mean, this is not, this is no longer like an elementary class like calculus, where you're just solving problems. Here, you have to be able to solve numerical problems, but you also have to be able to do a proof. So this, what I'm in the process of giving is the proof of the Chinese remainder theorem. So I just proved the first part of the theorem. If the GCD of A and B is 1, then for all integers alpha and beta, there exists an integer x such that x is congruent to alpha mod A, and x is also congruent to beta mod B. And suppose we have another number, x prime, which is also a solution of these equations. X prime is congruent to alpha mod A, and x prime is congruent to beta mod B. So by transitivity of congruences, x is congruent to alpha is congruent to x prime mod A. So A divides x minus x prime. Also, x is congruent to beta mod B, and beta is congruent to x prime mod B. So x is congruent to x prime, so B divides x minus x prime. So we have an integer x minus x prime, which is divisible by A and by B. But if the greatest common divisor of A and B is 1, that means that x minus x prime is divisible by their product, which means x is congruent to x prime mod AB. So the solution of the congruences in the Chinese remainder theorem is unique up to the product of the moduli. So let's just look at some examples. Suppose I want to solve x congruent to 2 mod 3 and x congruent to 4 mod 7. So I want to find one integer which solves these two congruences simultaneously. And we know we can do this because the GCD of 3 and 7 is 1. So we can use CRT, Chinese remainder theorem. And how? Well, if x is congruent to 2 mod 3, that means x is 2 plus 3 times y for some integer y, right? Every number that's congruent to 2 mod 3 can be written in this form. But then x, which is 2 plus 3y, must also satisfy the second congruence. This has to be congruent to 4 mod 7, which means subtract 2, 3y is congruent to 2 mod 7. So we have to find the solution of this congruence. And you can check the solution of this congruence is y, any number y congruent to 3 mod 7. Because if y is 3 mod 7, 3y is congruent to 3 times 3, which is 9, which is congruent to 2 mod 7. So y can be any number of the form 3 plus 7z. Any number that's congruent to 3 mod 7 is of this form. So x, which is 2 plus 3y, is 2 plus 3, and this is what y is, 3 plus 7z, 2 plus 9, this is 11, plus 21z. So any number x, which is congruent to 11 mod 21, should be a solution of this. Right? Should be a solution of these two congruences. So let's check. If we let x be equal to 11, 11 minus 2 is 9, which is 3 times 3. So 11 is congruent to 2 mod 3. And 11 minus 4 is 7. So 11 is congruent to 4 mod 7. So x equal to 11 is a solution of this pair of congruences. And this solution is unique modulo the product of 3 and 7, which is 21, which is why we saw that any number x congruent to 11 mod 21, every number in this congruence class is a solution, and only those numbers. So this is very important because the midterm, as you ask, will involve proofs as well as numerical problems. So this is a typical problem. And let me just emphasize this importance of this. I'll just do it again. All right. So we want to find a number x which is congruent to 2 mod 3, and at the same time is congruent to 4 mod 7. So we can say if x is 2 mod 3, x is 2 plus 3 times y. With any number congruent to 2 mod 3s of this form, but this number also must be congruent to 4 mod 7, which means 3y has to be congruent to 4 minus 2 mod 7, and a solution of this, the only solution of this congruence, is y congruent to 3 mod 7. So y is any number of the form 3 plus 7z. And so x, which is 2 plus 3y, is 2 plus 3, and this is my y, 3 plus 7z. That's 2 plus 9 plus 21z. or 11 plus 21z. That's my x. So x is any number congruent to 11 mod 21. And this congruence has the solution 11, and any number which is congruent to 11 mod 21 is a solution. Let's just check. Suppose I take, for example, x equal to 43. 43, sorry, x equal 53. So 53 minus 11 is 42, which is 2 times 21. So 53 is congruent to 11 mod 21. So 53 also has to be a solution of this congruence. Let's see, 53 minus 2 is 51. That's 3 times 17. So 53 is congruent to 2 mod 3. 53 minus 4 is 49. That's 7 times 7. So 53 is congruent to 4 mod 7. So 53 is another solution. All right, any questions about this? Let's do some more problems. Suppose I have, let's see, what are some, suppose I take A to be 8 and B to be 33. So the GCD, the greatest common divisor of 8 and 33, and make this more interesting. Let me make this 10. 10. So the greatest common divisor of 10 and 33 is 1. So I want to solve a pair of congruences where x is congruent to something, let's say mod 10, and x is also congruent to something else, mod 33. So what numbers can I pick here? I can put anything there. So someone give me an integer, positive, negative, whatever. Anyone have a favorite integer? Just unmute and tell me an integer.
Can we say 2?
2, okay, no objection to 2. And I need another integer.
-7.
-7, excellent choice. So I want to find a number which is congruent to 2 mod 10 and simultaneously congruent to -7 mod 33. So let's apply the method I used a moment ago. So if x is congruent to 2 mod 10, if and only if x is 2 plus some multiple of 10. That's what it means for x to be congruent to 2 mod 10. And x is congruent to -7 mod 33, and x is a number of this form, means 2 plus 10y, that's my x, is congruent to -7 mod 33. So I have to satisfy this congruence. So if I subtract 2, that says that 10y is congruent to -7 minus 2, or -9 mod 33. So I have to find a number such that 10y is congruent to minus 9 mod 33. Now, how do we do that? Right. So the next step is to solve 10y congruent to minus 9 mod 33. So how do we solve a congruence like that? Well, there's a number of different ways to try. You might use, let's say, trial and error. So you might make a table, given y, what is 10y congruent to mod 33? So for example, if y were 0, this would be 0, not minus 9. If y were 1, this would be 10, right? 10 times 1 is 10, which is, again, this is not congruent to minus 9, or minus 9 is the same as 24, right? Because 9 plus 24 is 33. For 2, we get 20. That's not congruent to minus 9 or 24. Doesn't work. 3, we get 30. 30 is not congruent to 24. 4, we get 40. 40 is congruent to 7. It's not congruent to 24. We could try all these numbers, and we'd have to do 33 attempts, and if we're lucky, we might find an answer quickly. If we're not lucky, we might find an answer after only a lot of work. So we might try another method. And the other method, which is similar to what we used in the proof, is because 10 and 33 are relatively prime, you can write the greatest common divisor 1 as 10s plus 33t. We want to be able to, can we solve this congruence? So one way to do, well, the easiest way is, if you're just lucky, you could see that like 10 times 10 is 100, minus 99 is 1. So if you let s equal to 10 and t equal to minus 3, you get 1 is 10 times 10 plus 33 times minus 3 is 100 minus 99. That's equal to 1. So 10 minus 33, 10s, 10 times 10 plus 33 times minus 3, that works. And then we would write 2 minus 7, which is 2 plus 7, is 9, is 9 times 1, which is 9 times this 10s plus 33t, which is trying to think if there's a less, a way to do this with this calculation. Let me just take a clean piece of paper so I have more room here. So this is the problem I'm trying to solve. X congruent to 2 mod 10 and X congruent to minus 7 mod 33. And because the moduli 10 and 33 are relatively prime, the Chinese remainder theorem guarantees a solution, and which will actually be unique modulo the product of these two numbers, 10 and 33, modulo 333. So there's a unique integer between 1 and 330 which solves these two congruences. And we want to find it. So we know that 1 can be written as 10s plus 33t, where we take s equal to 10 and t equal to minus 3. Because 10 times 10 plus 33 times minus 3, that's 100 minus 99, that is equal to 1. So I can write 1 is 10s minus 32t. And in the so if I take 2 minus minus 7, which is 2 plus 7, which is 9, this is equal to 9 times 1, which is 9 times 10 times 10 plus 33 times minus 3, which is 90 times 10 minus 27 times 33. So what I'm trying to do is repeat the proof that I gave for the Chinese remainder theorem originally. Let me just put this in a box here so you can see what I'm doing. Remember, we had x minus congruent to alpha mod A and x congruent to beta mod B, where A and B were relatively prime, so I could write 1 as SA plus TB. So if I multiply this by beta minus alpha, I get beta minus alpha is beta minus alpha S times A plus beta minus alpha T times B. So beta is equal to alpha plus beta minus alpha SA plus beta minus alpha TB. And if I call this number X, then beta is X plus beta minus alpha TB. So beta, X is congruent to beta mod B. And if this is X, you can see from looking at this that X is also congruent to alpha mod A. That's how I prove the Chinese remainder theorem. So here I have my modulus A is equal to 10. My second modulus B is 33. My number alpha is 2. My number beta is minus 7. And I'm going to let X be equal to alpha plus beta minus alpha SA. My S is S is equal to 10, and I don't need it, but T was equal to -3. So alpha plus beta minus alpha SA, alpha is 2, plus beta minus alpha is -9 times S, which is 10, times A, which is 10. So this is equal to 2 minus 900, or minus 898. So we get a number X equal to minus 898. Well, it's a funny number to come up with, you might think, but let's see if it works. So we want to solve the congruence, X congruent to 2 mod 10, and simultaneously X congruent to -7 mod 33. And we said X equal to minus 898 should be a solution, if my arithmetic is correct. So let's check. X minus 2 is minus 898 minus 2 is minus 900, which is definitely divisible by 10. So the first congruence works. And X minus 7 is X plus 7. So that's minus 898 plus 7 is minus 891. Is that divisible by 33? I have no idea. So if I divide 33 into 891, this goes 2 times, that's 66. I get 132, and 7 times 33, 7 threes are 21, 21 plus, works perfectly. So 891 is 33 times minus 27. So X is also congruent to -7 mod 33. So that's a solution, minus 898. And any solution, X, is going to be congruent to minus 898 modulo the product of these moduli, 10 times 33. Or in other words, X is congruent to minus 898 modulo 330. Let's see, what's the least non-negative residue of minus 898 modulo 330? So 3 times 330 is 990. So it looks like this should be congruent to 92 mod 330. Because 92 minus 898 is 92 plus 898 is 990 is 33 times 10, or 330 times 3. Let's check if 92 works. That's a more interesting calculation. 92 is congruent to 2 mod 10, because 92 minus 2 is 90. It's 10 times 9. And 92 is congruent to -7 mod 33, because 92 minus -7 is 92 plus 7 is 99, is 33 times 3. So the least positive solution of this pair of congruences is 92. All right. All right. Let's do another example. So suppose I want to solve x congruent to 4 mod 7 and x congruent to
Professor,
yes,
how did you get 92?
okay, let's go back and look. Um, so we're trying to solve the congruences. X congruent to 2 mod 10 and x congruent to minus 7 mod 33. And the first thing we did was we saw that one solution of this pair of congruences is x equal to minus 898. Then we use the general theory, which tells us that any integer x prime such that x prime is congruent to minus 898 modulo the product of these two moduli, 10 times 33, which is 330, is also a solution. Okay? So minus 898 is a solution, but anything congruent to 898 modulo 330 is a solution. So then I was curious, I looked for I wanted to find the least non-negative residue, the smallest non-negative integer, x prime, congruent to minus 898 modulo 330. So, for example, if I take 3 times 330, that's 990. So for example, x prime equals minus 898 plus 990. These are certainly congruent modulo 330. And this number, 898, 990 minus 898 is 92.
Can you move it up a little bit? I'm sorry.
Right. So 990 minus 898 is 92. So 92, that is 92 is congruent to minus 898 modulo 330. So 92 is a solution, and 92 is certainly the smallest number, the smallest integer in this congruence class modulo 330. That's how I found 92. I found one solution, which is perfectly good. A correct answer to the problem is minus 898. If you wanted to find the smallest positive number or the smallest non-negative integer, that's a solution. That would turn out to be 92. All right. All right, so here's another problem. Suppose I want to find, I look at the pair of congruences, x congruent to 4 mod 7 and x congruent to, let's say, 3 mod 5. So there are two problems. Find a solution, any solution, find all solutions. And we can also say, find the smallest positive solution. So spend a minute or two. Looking at this. Let me just pause the record. So work this out, and I'll give you a couple minutes and then I'll try to do it. Okay. Does anyone have a solution? So let me write this problem down again so I have some more space. I want to solve the pair of congruents as x congruent to 4 mod 7 and x congruent to 3 mod 5. So from the first congruence, we know that x has to be an integer of the form 4 plus 7y. A number is congruent to 4 mod 7 if and only if it can be written in this form. But this number also must be congruent to 3 mod 5. So we want to find y that solves this congruence. This is the same as 7y congruent to 3 minus 4 or minus 1 mod 5. Of course, 7 is the same as 2 mod 5. So this is the same as find y such that 2y is congruent to minus 1 mod 5, or minus 1 is the same as 4. 2y is congruent to 4 mod 5. So just doing very elementary arithmetic, a number y that satisfies this congruence is any number such that 2y is congruent to 4 mod 5, and you can tell by looking that y is 2, is the solution, because 2 times 2 is 4. So any number y congruent to 2 mod 5 will be a solution. That means y is any number of the form 2 plus 5 times z for any integer z. And so x, which is 4 plus 7y, that's 4 plus 7 times 2 plus 5z. 7 times 2 is 14, plus 4 is 18, plus 35z. So x is any number of the form 18 plus 35z. So the simplest solution is 18, which is also going to be the least positive solution. I mean, the set of all solutions will be all numbers x congruent to 18 mod 35, and the least positive solution will be 18. So let's check. 18 has to satisfy these two congruences. So 18 is congruent to 4 mod 7 because 18 minus 4 is 14 is divisible by 7. And 18 is congruent to 3 mod 5 because 18 minus 3 is 15, which is 5 times 3 is divisible by 5. So 18 is the solution of both of my congruences, and it's the least positive solution. So that's very nice, and that's it.
How did you get 2y?
Sorry?
How did you get 2y?
Here?
Yeah,
So 7 is congruent to 2 mod 5, because 7 minus 2 is 5.
okay.
So 7, but you can multiply congruences. So 7 times the number y is always the same as 2y mod 5. So I can replace 7y by 2y. They're the same numbers. They're congruent modulo 5. 7 is congruent to 2 mod 5. So 7y is congruent to 2y mod 5. I could have put in lots of different numbers here. For example, 7 is congruent to 17 mod 5. So I could put 17y here, only that only makes things more complicated and not less complicated. So I just tried to find the smallest number and see what would happen. Any other questions about this? Okay. So let's go on to section 1.8, which is the next topic. And this has to do with polynomials. So this is section 1.8. And polynomials are things you have been using for a long time. In calculus, they were the simplest functions to differentiate. And a polynomial is some expression of the form, let's say, an x to the n, an minus 1 x to the n minus 1. You start with some positive power or non-negative power of x, and you have this expression in powers of x from the nth power down to the 0th power. X to the 0 is 1, right? X to the first power is x, and so on. So this is a polynomial, like 7x third x cubed minus 2x squared plus 5x plus 1,000 is a polynomial. Even 0 times x third plus 5x squared minus plus 0 times x plus 11, this is another polynomial. And what is called the degree of the polynomial is the highest power of x that you see in the polynomial with a non-zero coefficient. So in this polynomial, the highest power of x is x cubed, and the coefficient is 7, is non-zero. So this polynomial is degree 3. Here I have x cubed, but with a coefficient of 0. Here I have x squared with a coefficient of 5. So the highest power of x with a non-zero coefficient for the second polynomial is 2. So this polynomial has degree 3, and this polynomial has degree 2. I mean, polynomials are really the simplest functions there are for us. And you learn in pre-calculus how to add polynomials. If you have 2x cubed plus 7x plus 9 is one polynomial, and 5x squared plus 3x minus 11 is another polynomial. You just add the corresponding powers of x. So here I have 2x cubed. Here I have 5x squared. Here I have 7x and 3x. And here for the constant terms, I have 9 minus 11. So this is 2x cubed plus 5x squared plus 10x minus 2. And you multiply polynomials, and of course, you subtract polynomials term by term the same way. How do you multiply polynomials? Well, you really just distribute across. So if I had to multiply 2x cubed plus 7x plus 9 times 5x squared plus 3x minus 11, this would be 2x cubed times this. Let me just do it in several steps. 2x cubed times 5x squared plus 3x minus 11 plus 7x times 5x squared plus 3x minus 11 plus 9 times 5x squared plus 3x minus 11. This is what? 2x cubed times this term by term. I get 10x to the 5th plus 6x to the 4th minus 22x cubed. Here I get 5 times 7 plus 35x cubed plus 21x squared minus 77 times x plus 45x squared plus 27x minus 99. And then I collect the terms. I have one term of degree 5, one term of degree 4. I have two cubic terms, minus 22 and 35, which is plus 13x cubed. I have two quadratic terms with coefficients 21 and 45. So that makes 66x squared. I have two linear terms, minus 77 plus 27. That makes minus 50x. And I have one constant term, minus 99. So you're expected to know high school algebra and be able to do elementary stuff like this. Okay. Just to make one other obvious fact, if I have the polynomial, let's call it, say, p of x equal 3x squared minus 7x plus 2. That's the same as the polynomial 0 times x cubed plus 3x squared minus 7x plus 2. It's the same as 0 times x to the 4th plus 0 times x cubed plus 3x squared minus 7x plus 2. In fact, you can often think of as a polynomial as having infinitely many terms, but only finitely many of the terms have non-zero coefficients. So these are all the same polynomial. And so if I have to add two polynomials, so I can assume they're of the same degree just to make the notation easier. suppose P of x is an x to the n, an minus 1 x to the n minus 1, plus a1 x plus a0, and Q of x is bn x to the n, plus bn minus 1 x to the n minus 1, plus b1x plus b0. I add the polynomials by just adding term by term. So the coefficient of x to the n will be an plus bn. And the coefficient of x to the n minus 1 will be an minus 1 plus bn minus 1. Down to finally a1 plus b1 times x plus a naught plus b naught. So that's the simple formula for addition. And the formula for multiplication is slightly more complicated when you write it out. So you're going to multiply these polynomials. I don't have to assume they're the same degree, but when you distribute this, you get all possible terms of the form ai x to the I and bj x to the j, where I goes from 0 to n and j goes from 0 to n, all possible terms. But then you can collect the terms. So this is really the same as a sum over all I and j, ai bj x to the I plus j, plus x to the I times x to the j is x to the I plus j. And what is the coefficient of x to the k going to be? So this is a sum over k. When do you get x to the k? When I plus j adds up to k. So if I look at the sum of all ai bj, where I plus j equals k times x to the k, this is going to be the coefficient of x to the k, and k goes from 0 up to n plus n, or however high it goes up. So, or another way to write this is the sum over all k, sum over, now if I plus j equals k, that's the same as saying that j is k minus I. So I could just sum I goes from 0 up to k, a sub I, b sub k minus I, x to the k. And that's the formula that you'll see written out in the text. So you can add, subtract, and multiply polynomials, but you can't necessarily divide one polynomial evenly by another. But there is, just the way we have long division for integers, we have long division for polynomials. So let's make one observation first. Remember, the degree of the polynomial f, this is the highest power of x in f of x. And the highest power means the highest power with a non-zero coefficient. So if f of x is 7x cubed plus 2x minus 9, this has degree 3. And if g of x is minus 5x squared plus 11, this has degree 2. The fact that there's no quadratic term here or linear term here is irrelevant. You're just looking for the highest power of x with a non-zero coefficient. And if you multiply these polynomials, you're going to get, well, you're going to get 5 minus 5 times 7 minus 35x to the 5th plus some bunch of terms, and the constant term is going to be minus 99. So here the highest power of x is 5. This is degree 5. And this is a general phenomenon. If you have two polynomials f and g, the degree of the product, if they're non-zero, the degree of the product is the sum of the degrees. So f has degree 3, g has degree 2. The product has degree 3 plus 2, or 5. And if you take f plus or minus g, you're not going to get any higher power of x in the sum or the difference than occurs in either f or g. So this is at most the maximum of the degree of f and the degree of g. All right. Any questions about that? So we have the definition of divisibility of polynomials. So a polynomial f divides a polynomial g if there is a polynomial q. Such that g is f times q. So, for example, x minus 2 divides x plus x minus 6, I think, because, so this is my g, and this is my f, because x squared plus x minus 6 is x minus 2 times x plus 3. Here's g, here's f, sorry, let me call this f. This is g. Because, yeah, g is f times x plus 3. So this is my quotient polynomial q. So x minus 2 divides x squared plus x minus 6. Let's see. So here's a question. Does x plus 1 divide x squared plus 1? Does x plus 1 divide x cubed plus 1? Does the polynomial x squared plus 2x squared plus 1 factor? Does x squared plus x squared plus 1 factor? Factor means f factors, if or g factors, if you can write f as g as a product of two polynomials, just the way for integers, like you say 6 factors because it's 2 times 3. So you might say x squared minus 1 factors because it's x plus 1, x minus 1. So do either of these polynomial factors, does x plus 1 divide this, or does it divide this? Interesting. So think about those questions for a minute. And an important definition is this is analogous to a prime number, but we use the word irreducible for polynomials. A polynomial is called irreducible if it is not the product of polynomials, both of degree at least 1. So to ask if a polynomial factors is the same as asking if the polynomial is irreducible. Ooh, any success? Does x plus 1 divide x squared plus 1? So if x squared plus 1 is x plus 1 times some other polynomial f of x, this has degree 2, this has degree 1, so this will also have to have degree 1 because the product of these two polynomials has degree, sum of degree of f plus sum of this, that's the degree of this plus 1 is 2. So the only number, so 1 plus 1 is 2, this has to have degree 1. So then the degree of f of x is 1, so f of x has to be ax plus b with a different from 0. So then you would have to have x squared plus 1 is x plus 1 times ax plus b, which when you multiply this out is ax squared plus a plus bx plus b. And if this is equal to x squared plus 1, that says that a, this has coefficient 1, this has to be 1. This has constant term 1, so b has to be 1. But here the coefficient of x is 0, so this would have to be 0. So if the factors 1 plus 1, a plus b, which is 1 plus 1, which is 2, is equal to 0, which is impossible. So to assume there's a factorization leads to this contradiction. So the answer to this question is no. X plus 1 does not divide x squared plus 1. Does x plus 1 divide x cubed plus 1? I don't know. If you take x plus 1 times x squared minus x plus 1, you get x cubed, x squared minus x squared, x minus x plus 1. Ah, this is a factorization. So the answer is yes, right? This is x cubed plus 1 is x plus 1 times this. This is the quotient when you divide. So x plus 1 does divide x cubed plus 1. Does x squared, oh, I should have said this is, yeah. Does x squared plus 2x plus 1 factor? Well, this is just x plus 1 squared, or x plus 1 times x plus 1. And what I meant to ask for the second was really this. Suppose I take x to the 4th plus x squared plus 1. Sorry, if I made this x to the 4th plus 2x squared plus 1, that would be x squared plus 1 times x squared plus 1. So this factors. X to the 4th plus 2x squared plus 1 is x squared plus 1 squared. What about if I have instead of a 2, a 1 there? Does x to the 4th plus x squared plus 1 factor? Oh, that's a good question, actually. Maybe I'll leave that for you to think about for Wednesday. So what you need to begin to study this week, if you haven't been reading ahead, is this section 1.8 on polynomials. Polynomials are extremely, extremely important in algebra. And yeah. Any questions about anything that we've done today? Okay. Then we'll stop. Supposed to be bad weather tomorrow, so stay warm, stay dry. I have an office hour problem session tonight at 7, and next class is Wednesday at 9 o'clock. See you then. Bye all.